word, it says introduction. So why are we doing this? So based on the several years of professional experience that I have had in engineering, I noticed that something very common in most of the engineering projects is that when you look at them from the perspective of the technology readiness level, usually 1 and 2, TRL 1 and 2, are either used in the internal R&D branches of the company with in collaboration with university, national labs, etc. Unless there is a continuum between the internal R&D or R&D in general and the engineers who will take care of walking the project from TRL 3 to TRL 6, then what happens is that the potential for innovation, implementing innovation in the project falls into what is called by many the valley of death. And in the valley of death, in TRL 5, usually where you get the experimental prototype. In TRL 6 is the engineering prototype that is taken to the field. And then finally, in TRL 8 or 9, you do the commercialization. So what I have noticed is that there are many people, like for example, Simon, who have a very good experience on walking through the valley of death. So the objective, the general objective of this type of, let's call colloquiums, is to have people like Simon, and we will invite more people to share with us how their experience, some cases, sharing with us how they have been able to walk through the valley of death. Now, personally, I have had the opportunity to work in several projects in which I was able to use 3D printing. Here we have 3 cases. One was related to the design of autonomous underwater vehicles. Another one was related to gas turbines, and another one was for equipment for oil and gas exploration. In the first of the 3 cases, I found that using 3D printing was going to allow us to reduce by almost 2/3 the length of a underwater vehicle that we were designing. And I found, I was very surprised that actually that time, it was about 3 years ago, we could print some components in steel 17.4, and that was a key enabler of that, implementing that design. In the area of gas turbines, there were a number of problems that they were having, and I found that 3D printing of machine elements that were compliant in the sense that they were elastic, was feasible only by using 3D printing. Feasible in the sense of manufacturing and cost. And also, I have had experience of exploring the use of 3D printing for components that are used in the oil and gas exploration, and they can withstand 500 Fahrenheit and 30,000 PSI. So I will leave it there just to let you know that I professionally have worked with 3D printing, and I have found it to be a quite viable engineering solution. Now, I just want to remark that there are 3 aspects of aluminum, which is the material that Simon will focus on today, which are, number 1, is abundant. It has a very high capability for being recycled, and is both light in weight as well as strong. So Simon, you have the floor now. But before that, I just want to tell you that my group, its name is Cambridge Research and Technology. And if you feel like you want to converse more about this or suggest other topics for conversations, Here you have the website, you have the email, and you can also find us in LinkedIn. So I will proceed to stop sharing this slide, and then Simon can share his. Okay. Oh, by the way, Matt, while Simon is connecting, Matt Woods is connecting. Hello, Matt. How are you today?
Hi, I'm good, thanks. How are you?
Fine and dandy. Matt, could you use 30 seconds to tell us, where you are, what you do, so the rest of the group can learn a bit more about you, please?
Sure, absolutely. Thanks, Julio.
Yeah.
Appreciate you having me on here. And yeah, I'm located in State College, Pennsylvania. We're right next to Penn State University. This is where I founded the company Exact Metal, and we're basically focusing on innovating in the metal 3D printing space, particularly powder bed fusion, and focusing on bringing down the cost barrier to entry and offering more accessible technology that offers the same type of performance as higher end investments would in the same space. So yeah, we're excited to learn about new developments in the space, and so yeah, looking forward to hearing what you have to.
Very good.
Yeah.
Very good. Matt, thank you very much. Just to remind you that the scope of this conversation is more like a colloquium, and there will be more presentations, and you should feel free to contact me either to suggest another presentation, or if you want to talk about business, we can also do that, okay? So without more introduction, Simon, you have the floor. Good luck and enjoy. Have a lot of fun presenting.
All right. Thanks, Julio. Hi, all. Happy New Year. My name is Simon Poon, and really it's my pleasure to be able to speak with you briefly. We're limited by the hour, but on this platform today about 3D printing with aluminum. You guys can see my slides, all right?
Yeah, but it is not in presentation mode yet. If you, I don't know if you're aware.
Oh, actually, I'm connected to 3 screens, so if okay, I want to just present this way. Maybe I.
Yeah, but fine. You use whatever you can present however you want.
To like.
Yeah.
Just
okay.
Okay. Yeah. So okay, continue on. There will be many messages conveyed today, but one particular message that I would like us to walk away with today is that typical commercial aluminum alloys cannot be easily 3D printed, and those that can be 3D printed are very limiting in application and in many cases lack structural capabilities. So it's important for us to understand the current landscape and the future demand for new alloy design. And you may ask why we care so much about aluminum, and to many engineers, it's plain and simple. It's about cost and efficiency. As engineers, we understand the vast usage of aluminum alloys, especially in the aerospace, commercial aerospace industry. But for those in the automotive sector, you may also see a push in the past 5 years towards lightweighting and the trend to switch from a traditional steel material body to a multi-material design, making of steel and aluminum alloys, and even composites in some high-performance vehicles. And just expanding a little bit more in lightweighting, we've seen the emergence of generative structural design by intelligent software that leverages topological optimization. And these designs are really made possible in production through large-scale additive manufacturing, or also known as 3D printing. So in my past 4 years of experience working in automotive industry, lightweighting has increasingly become an important and growing design factor, where generative design enables lightweighting via 3D printing. But then again, since not every material or every aluminum can be 3D printed, there's great demand to create one's own. And I will show you a couple of examples of who's doing that in the industry, and finally a case study of how we use our own, how we create our own aluminum for our hypercar at Divergent. And for those who are not familiar with generative design, it just refers to a iterative design process with known constraints. So for example, here in the lower right corner, left corner, you see a control arm that was a hunk of metal. but with generative design approach, this part has been trimmed and hollowed out, but still meeting the, the preset constraints requirements. So now it's 80% lighter or so. So you may hear me reference an article called "The Confessions of a Capital Junkie," written by Sergio Massioni throughout my presentation. Sergio Massioni is the late chairman of Fiat Chrysler Automotive, who really took a hard look on the future of manufacturing, and particularly in the automotive sector. But from his writing, I learned to provide upfront what the presentation is about and not about. So here it is. The goal is to simply provide insight on the state of the art. Like Julio shared, this colloquium. We're among friends, and those like-minded, and it's a platform for us to share. How I would say that I was inspired by Sergio Massioni to make these confessions and just share with the community where I see the most pain lies. So what this is not about is not a sales pitch. I'm not selling anything. And I'm not trying to make a recommendation for what material or which vendor to use. What this is really about is why aluminum is important. Give an overview landscape of 3D printable aluminum alloys today that are available to the market, and then show a user case on the proprietary aluminum alloys. So with that, shameless plug here. I understand that there will be a Q&A discussion at the end, and I like to be as useful as possible answering any questions. So just a brief introduction of my background. I'll start from the bottom. I became really interested in academic research, even when I was an undergraduate at UC Irvine. Eventually, I pursued a graduate degree in material science. I started out with aerospace engineering over at UC Santa Barbara, where I had an opportunity to work on new materials for a nuclear fusion reactor design. This is the tokamak. Apologize if it's too small, but it looks like a donut. If you are the empty space looks like a donut here. So I was responsible for, or my research group was responsible for creating the first wall material. So actually, where the material sees the first reaction of the fusion. So for high temperature material. Then I actually got my first exposure, first taste of 3D printing when I was R&D staff at 3M. And there I was given a third hand, if not fourth hand, binder jet printer to first fix up and then and make it work and print with 3M's proprietary ceramic material at the time for dental applications. Then later on, I finally joined Aerojet Rocketdyne, where I really saw large-scale usage of additive manufacturing, where I was primarily working on the AR1 booster engine program and supporting the combustion devices team. And here's a picture of the subscale rocket engine there on a hot fire test. And a lot of the components there were 3D printed. And Aerojet Rocketdyne also had their proprietary alloy called Mondalloy, which I'm assuming some of the audience are very familiar with. Then one day I got a call from a recruiter and headhunter, essentially moved me over to Divergent 3D. I've been here for over 4 years now, a little bit after Series A. So I've seen a lot of growth and a lot of learning in the in the field and in the 3D printing field and tech field and automotive. But here I lead a team of scientists and engineers to do materials work. We built out our own materials lab, so we have testing capabilities, characterization capabilities, and we also spent the past 2 years to make our own alloys. And I'll share a little bit of that in the case study. But yeah, it's a quick background. So I'm open book, and anything I'm allowed to say I will share. But let's jump into something more interesting and why aluminum is important. So in this slide, I will address the 3 pillars that Julio also mentioned that support the aluminum business case. First, aluminum is very abundant. Pay attention for a second on the table on the right here. That after oxygen and silicon, aluminum is actually the most abundant element that we have direct access to today. In a world where pricing is more competitive than ever, aluminum is shown to have an advantage over conventional materials like steel if mechanical properties can be matched. The second is its recyclability. According to aluminum.org, aluminum is 100% recyclable and sustainable. A perfect example of a circular economy where we strive to achieve zero waste and minimal impact on the environment. Also, the aluminum recycling infrastructure is very well established. Personally, I would say that the 100% recycling, rhetoric from the aluminum.org assumes that we'll forever be using aluminum cans because so I read their life cycle analysis and why they claim 100% recyclability. They're assuming the assumption is that all the scrap metal from cars, from planes, from other applications, consumer electronics, they all boil down to aluminum cans, which we use for beverages and others. But the assumption is we use cans forever. Hence, it's 100% recyclable. Third pillar is lightweighting. Speaking again on the trend of lightweighting, aerospace and automotive alike, OEMs are trending to reduce vehicle weight because lightweighting makes the vehicle more energy efficient. By using a highly recyclable material such as aluminum, OEMs are now able to meet the growing government regulation demands, right, for a circular economy, while making vehicles more energy efficient for the consumers. If you're using a gas vehicle, actually EVs also, the lighter the car, the less energy it takes to propel. Just some examples, which I will also touch on later. OEMs like Chevy, Ford, and Tesla, among others, have already invested in their fully aluminum-made bodies. So again, the 3 pillars, why aluminum makes aluminum important given the case, its abundance, highly recyclable, and lightweight. So in order to unlock lightweighting, generative design should be used, which brings us back to 3D printing and why it's important, because it allows for complex shape production. And as I've said before, not all materials are 3D printable and not all aluminums are 3D printable. So depending on how far along a company is to integrate 3D printing in their production line, one may have different mechanical property needs. To not go too far, like if a company is creating or is decided to 3D print parts, without any heat treatment or post-processing, I just want to use that as a crash bumper. Versus another company that's not, obviously the company that decides to use the printed material as a crash bumper would have different requirements than the one that doesn't. So in this case, Divergent, we're crazy enough to think and prove actually that we're able to do that, to print a crash-worthy material. Let's look at the landscape though. Currently in the slide, you can see a list of commercial aluminum alloys. ASI 10mg, and I can tell a short story on this material. It's I think its trade name is also known as A346 in the Aluminum Association, which is really a well wire composition, and it's developed and used in 3D printing originally to show to essentially enable a showcase of of 3D printing technology. So the people who are selling the printers at the time don't care about the material integration integrity at the time. They wanted to show that I can have a powder bed, shoot laser, and get a 3D a printed object. So so they chose a non-proprietary aluminum alloy that's easily printable, and then the supply chain, so the powder makers are incentivized to make this because they don't have to pay someone else a premium to use this material or license material, like in the case of AP Works. And then, if the audience is familiar with the other companies, startups, national labs, they sometimes they charge a fee, right, for you to license their composition and utilize their patents. So so ASI 10mg non-proprietary, the supply chain is incentivized to do that. So which they did. Now almost every powder maker that does aluminum today, they make this material. Because that's still the industry go-to for a prototype before they get into fancy designs and integrating this. So there are also common requirements that I've witnessed from end users, and those are three things: high strength and fatigue life, ability to hold a high strength and fatigue life in elevated temperature, and then also matching energy absorption capabilities to conventional material. So some of these other non-proprietary materials can actually meet these requirements. From literature, from experience, you can see, you can evaluate ASI 10mg, that it is very limiting. When you're, in my case, again, if you're make a crash bumper, the printed ASI 10mg would crash and shatter like glass, right? And even in the in our A pillar and B pillar, so the most stiff parts of our strongest parts of our vehicle, this material also does not meet the requirement. It just doesn't have that specific strength that we need. So here's a quick landscape. In the next slide is a chart that I made using published data. And another shameless plug here, we at Divergent, we have two proprietary materials that, or family actually, that we've created over the past 2 years. One targeting over the high strength, which is the A pillar, B pillars that I sort of mentioned earlier. The other family is targeting the energy absorption, so the crash application. And here we can see that like some of our success, we're close to scamalloy in terms of ductility, and the strength, very close to some of these other guys. They're high up in the strength regime. Another dimension that I didn't plot here is price. I understand that a lot of these companies are startup companies, so their pricing structure may be different depending on their partners or their customers. So it wouldn't be fair for me to disclose that information, but I can tell you that some of these materials, are 400 times more, not 400 times, 400% more than the AOSI 10mg, the typical here. So really the driver for Divergent, and I think in the next 10 years for many other players, they will also be motivated to either create their own materials, invest in their own internal R&D, or buy out one of these startup companies. Okay, so next couple of slides, I want to walk us through a case study what we are doing at Divergent. So to start, I like to give a quick introduction of what we're doing at Divergent. Divergent Divergent Technologies, Divergent 3D, DBA, is a technology licensing company. We're not an automotive company. We've gotten feedback that people think we were. We were at the LA Auto Show and the Detroit Auto Show, but we were there to demonstrate that with our DAPS, Divergent Adaptive Production System, we can 3D print an entire car chassis, and we're focused on 3D printing, structures of vehicles. So Divergent, we radically transform auto manufacturing economics and environmental impact using data-driven approach for design and building vehicle structures. I have a video that I like to share, so just let me reshare. So that was a quick teaser of what we're doing at Divergent. Kevin Singer, you saw the guy saluting at the end. He's our CEO. He's a serial entrepreneur who really came up with the vision of using advanced manufacturing and really adapts to redefine automaking. What I'm most proud of is with my team, the past couple of years, we were able to work with our structural vehicle integration team to understand some of the pains that they are experiencing. So in the next slide here, I wanted to just show a quick method of how what made us decide to create our own material. And in the next slide after this one, I'll show you some knowledge-based models on how we did it. So here, the first step is to define design requirements. So we work cross-function with the auto structures team and the vehicle integration team to understand that, well, to truly take advantage of generative design and 3D printing and be a pioneer in the field, what are some of the most attractive and to them, the low-hanging fruit, to make us, truly pioneer and proprietary. And basically, there are three requirements that we boil down to: crash-worthy. Like I said earlier, we want to be able to 3D print a part from our printer. Remove the support structures, depowder, and quickly be able to assemble that in our vehicle, in our structure. So I won't get into the specific numbers, but the high ductility, typical aluminum strength, energy absorbing for our crash bumper, our side bumper, our back bumpers. So though we boiled these requirements down to like a specific yield strength, tensile strength number, elongation, and energy absorption. like many other automotive companies, we also invest in triaxiality programs. So truly understanding the stress state of the material at a high strain rate. And then we create a material card. So then our structures team can use in their FEA analysis. Mentioned the control arms and the A pillars and B pillars. Those are very fatigue sensitive and high strength. Required components, places. So with these two big topics, we go back to, and open our books and engineered a truly 3D printable aluminum alloy that can meet these requirements. We've published in 2017 that we use aluminum alloys and titanium alloys for lightweight purposes. But you might be able to guess that with our growing materials team and some of the success we've had, we're trying to go towards all aluminum. Wherever it makes sense, because titanium does have a much higher stiffness than aluminum. So in some parts we may still consider titanium, but aluminum's cheaper. For in an automotive, its cost is very sensitive. So we're trending towards aluminum. So a little bit of what my team did was coming up with a governing model when we're making these from ground up new materials. So let's take a high strength requirement, for example. We would build a material model and validate the model's accuracy using tested data. And then we would refine again and again until we're satisfied with the prediction accuracy. So we have here in 3 steps, creating and validating governing model. With this model, with our understanding, we survey the periodic table for solid elements, and then we would optimize our process parameters to first see if the material is printable, and if so, we go through a design of experiments to make sure that the parameters are producing the right microstructure that gives us our properties, and also its production rate. So the fundamental, so going back, just looking at the governing model piece, the fundamental strengthening models are used. So like solid solution strengthening, precipitation strengthening, or dispersory hardening, grain boundary strengthening models are used. Solute elements are selected from the periodic table, and the alloy strength, in this case, in the high strength alloy family scenario, right? The strength is calculated from the optimized model, and then with what we think the most promising alloy recipe, we would go out to a powder maker and ask them to make 50 kilograms of this material, and we would actually print in our divergent facility, in our R&D 3D printers, and then we would also test in-house. So we own the whole process from modeling alloy and then choosing what's the most likable to succeed. Going to and then we outsource the powder making part. And once we have the powder, we would optimize our process parameters. So that was quite a iterative process. We've, I think, tried over 200 or more now, different compositions. And we were able to succeed in 2 families, so 2 series of aluminum for high strength and ductility. So yeah, but that was a lot of fun, and now we're in a position to optimize process parameters, where we're in the automotive industry, and we're competing against conventional automotive making or manufacturing techniques. So we even if we know that we can have advantage in strength and ductility and other properties, and weight, of course, through generative design. Speed also matters a lot, because speed means time, a reduction in time, and time means money. Automotive sector is super sensitive to price. So now we were really trying to increase the speed of printing our own material. Let's go to the next one. So I'd like to leave the group here before we go to open a discussion, some predictions that I have. Actually, the first one is not new. The growth of proprietary aluminum alloy development will continue in automotive for multi-material body purposes. I think the first institution that coined the idea was the Fraunhofer Institute in Germany. A long time ago, they proposed a multi-material body concept, and they actually succeeded in making some prototypes using steel and aluminum and titanium body material. But recently we saw that Tesla also came up with their own proprietary aluminum material for die cast purposes, and their pain point was that the traditional, I think, A356, is the aluminum alloy that they're using, what they were using. It's not conductive enough for them because they're EV, so they create their own. And with the adaptation of 3D printing and trend of EV, I'm predicting that there will be more of this type of activities going on. This is a patent just published by Tesla in 2020 February. So we can expect to see more of this. According to USPTO, consumer electronics still dominate the patent filing and publishing. So I believe this was a 2017 patent by Apple. Apple being the innovator in consumer electronic space, have continuously filed patents in the materials regime, and they will continue to do so as they have shown today. You can type in Apple Inc. in Google Patents, and you can see their families of 7,000 series aluminum modified and 5,000. And if you're an early adapter to technology like me, if you have the first couple of generation of the Apple iPhone or iWatch, they were first made out of steel. But because of the interest in aluminum and also their beliefs in its abundance, recyclability, and lightweighting, they also invested in proprietary aluminum alloys. Touching a little bit on what Julio said in the beginning on TRL, like startup companies, internal research, or national labs usually sort of define the future, right, of where the technology is heading. So AM production rate and material quality, if they are able to become competitive with conventional manufacturing techniques, that will eventually force the big guys, OEMs and other industry giants to either invest in development of their own printable materials, or buy out some of the startups. And current leaders in this field are, if you're familiar, Oak Ridge National Lab, I think they had aluminum series of aluminum alloys, 3D printable. JPL, they're printing a lot of parts on the Mars rover. Metallic glass, I think, is popular there. And some research institute, education institute, a lot of the professors and principal investigators also invested in making new printable aluminum. So with that, I'd like to thank everybody for the past 40 minutes of listening, and I'm glad to take any questions and open up for discussion. Julio?
Thank you very much, Simon. I think it has been very good. I would like to invite all the participants to please either ask questions or share your thoughts about what you are doing or what you're about to do. You know, as valuable as the information that Simon has shared with us is to actually converse among us, right? So please, the floor is open for any of you to ask questions, make comments. I have 2, 3, but I will hold my mine until the end. So please go ahead and ask your questions. And I will make sure that everybody is everybody can unmute, okay? So we can hear each other. So who goes first? Okay, maybe we need some coffee. So what about Jonathan? What is your first question or your first comment about what Simon has kindly shared with us? Jonathan, I hope you can hear me.
Can you hear me now?
Yes, perfect. Please
Okay.
go ahead, Jonathan.
Yeah, so in metrology, you know, we do a lot of inspection work, also for additive manufacturing. And so this was more just informational for me. I was hoping to get some ideas of what was going on with the additive manufacturing world and see where it was going. And I think this was really beneficial. So I appreciate your time.
Okay, good. So Matt, maybe you have some more questions or comments, please.
Julio, if I may just...
Yeah, please, Simon, go ahead. So sorry about that.
No worries. We also do a lot of metrology work at Divergent. An example that I can give is, so the Hyperloop One project, before Hyperloop One was purchased by Virgin Group. So right, like Elon Musk had that, or resurfaced the idea of this, supersonic pod, and then he had a competition. But Hyperloop One, a startup company in LA, took the idea. Well, they won the competition, I think, and then they took the idea and really built out a good, true MVP of that concept, or from that concept, and then now they're sold to Virgin Group. But the first prototype, so the pod that they showed to, I forgot the CEO's name, Richard Branson, was actually built by us, and their requirement was 3D scan copies of each part that we would deliver. So my first year at Divergent, this was 2017, I actually spent a lot of time 3D scanning of these 3D printed parts, and then fitting the scan data on with the CAD to show any deviation, right, from the printing and from the assembly, and all that was packaged and delivered to the Hyperloop team. So that still that culture of making sure that dimensional accuracies are there in 3D printed parts are still very popular, I think, in the industry, and specifically for us. So we have a metrology team at Divergent where we do this type of work.
Excellent.
Great. I guess I'll chime in now. Yeah, great. Thanks for the presentation, Simon. It was well done, and I appreciated all the information that you provided. My question is, how do you factor in the reactivity of the aluminum powders, and how does that look, in affecting the cost trade-offs for investing in facilities versus using non-reactive alloys like steels and things like that that might not require as heavy an investment in safety and personal protective equipment and things like that?
Matt, that's a great question. So we have invested millions in actually building out a explosion-proof facility. So inside, at Divergent, we started out sort of in this like little garage, and then we took over a former FedEx facility, and inside there has the engineering team and the office floor. But then we had to strip out say like a quarter of the facility, and then we brought in contractors, EH&S specialists, the fire department, and we all built a explosion-proof facility to just house our 12, I think, 3D printers now from SLM Solutions, all laser bed powder fusion, printing aluminum. So there's a lot of investment in doing so. We believe that we can cut down the cost eventually, by working with suppliers and really developing a supply chain for this type of facility. A lot of the cost, really is driven by the regulation bodies. So especially in the city of LA, there are a lot of policies, regulations have to meet that actually convert to cost of this building. So speaking a little bit more in detail, so the humidity needs to be controlled under a certain amount, and the humidifier need to be more or cost more because we're in a relatively humid environment, right? We're kind of close to the beach. So some ideas that have flown was okay. Well, depending on the customers who want to adapt, manufacturing platform, if they're in India, right, where it's very humid, or if they're in maybe the Middle East where it's dry, we would recommend a different, maybe slight adjustment or modification of the entire blueprint of the factory, the micro factory, and that would have a specific cost related to just that printing facility as well.
Mm-hmm. That's great, thanks. Yeah, because for me, it's interesting to hear how people are addressing it individually, because it seems to be a fairly large barrier to entry. As I mentioned, my company is focused on reducing the barrier to entry to get more people using the technology. And of course, if you have to invest millions in a facility, it doesn't matter how cheap your printer is, because you're still going to have to spend a lot on making your whole facility built around it. So I'm always curious to hear how other people are addressing it, and how maybe we could reduce that barrier somehow and still keep it safe. Just thinking of things, crazy ideas like making aluminum powders that are less reactive. I wonder if that was on the bar at all, or different things like that. Just curious to hear if there's any innovations out there.
I have seen. I won't point out the manufacturer, but I've seen aluminum powder machines, on the shop floor before, and I was assured that that it's safe because the entire 3D printing, powder handling system is all in one and inert.
Mm-hmm.
So the external environment doesn't matter as much. Yeah.
Right. That's on like a one-off basis, right? That's like one customer. Yeah. Okay.
Yeah. But do you have like a specific solution to this problem?
No, not necessarily. I'm just, kind of spitballing here, and just, curious if anybody else is addressing it, because it is something that we, struggle to grapple with, and we sell, different variants of our machines that are either reactive or non-reactive rated, and that allows us to kind of straddle that value discrepancy, and if a customer is looking to just get into metal 3D printing for the first time, we'll usually and budget, if budget's a big concern, then we'll focus on, well, non-reactive powders would be a good solution for you because then it requires less investment in all the the explosion proof of the whole facility. And,
Right.
we do use the logic of the machine being inert keeps it safe to a certain respect. But, I think we haven't bridged the gap between that and not having to do a whole facility overhaul yet on the reactive side. So, I understand that it's totally up to the customer on how they handle it, but for us being an OEM, it's a little bit different. So just, looking at it from an industry perspective, how do we address this problem? But
yeah, well said.
That may be an interesting topic for more follow-up conversations and maybe even more presentations. I think it's a very important point. Simon, could you please go back to the slide where you have the three aspects? I think number 8 maybe. So we keep going up. Yeah, no. 6. Perfect. So I have 3 questions, and all of them are related to the implementation of products that use this technology. So you highlighted a point that I think is very important, which is speed or time that you invest. So could you give us what you can choose whatever parameters you want to communicate this, like usually how much time, ballpark, order of magnitude, do you need to print, let's say, something that is about, I don't know, let's say 1,000 cubic centimeters, or how much time do you use to print something that will weigh more or less 1 pound or 1 kilo, and how that time varies between the different bubbles that you have grouped in this slide?
Yeah, Julio, that's a great question. Because I want to answer that in a fundamental way from how that what you said, the print rate and the restrictions affected our design in Element. So I'll just pick 2 materials. For example, I'll pick the typical ALSI 10mg and Airbus as Scalmalloy. Airbus Scalmalloy has about 4% magnesium.
Yes.
And from our experience, 3D printing this material using laser bed powder fusion technology creates a lot of soot. So black smoke that comes out after you shoot laser on the powder, and that smoke, if not taken care of correctly, or before the next laser were to activate again and shoot again onto powder, you get these spatter. During our chemical analysis, there are different types of oxides and carbides that are byproducts from the sintering process, and they would land on subsequent material, which you can imagine as you 3D print this object in the Z direction, and you have these holes or these defects, if you will, embedded in the material. So your mechanical property is going to drop significantly. So that begs 2 questions, right? Like, how fast can I control my laser? So if I want to print fast, the first principle is, okay, you increase the laser speed and the recoding rate to get as much material deposit as possible and sinter as possible. But that logic is really limited by how fast you can get the smoke away, or to reduce the amount of the spatter creation. So we are tackling this from a fundamental standpoint by changing the chemistry, right? We have control over how much magnesium or whatever solute that we can add. So unlike Airbus, right, we we're probably going to want to stay away from high amounts of magnesium, where where a large amount of smoke can happen once interacted with the laser. So in terms of print speed, and with this logic, in mind, and how we design our divergent materials, we're printing about 20 times faster than the typical SI10MG. So that, if I was the AM CAD or the CAM engineer, I would be able to tell you the actual weight per hour.
Yeah.
But I think the rate that the SLM Solutions, which is our strategic partner, their data sheet, I think, says something like 30 milliliters per hour printing with this aluminum.
Mm-hmm.
So with that, if actually I take it back. We're not only 20 times more. We're more than that. I don't think I'm allowed to say how much exactly, but yeah, we're way past that.
But so it's at least an order of magnitude faster.
Yeah, so it's two orders of magnitude faster.
Okay. Yeah, you were familiar with it.
And even more from the Airbus alloy. But I gave the example of the Airbus, the magnesium, there to show a drastic improvement, and also a key sort of design decision on how we choose our solid elements.
Very good, very good. Yuping, could you please share with us or present a question, or share with us any comment that you have? We're very interested on your comments and questions, please. Yuping?
Oh, sorry, I was
you were in mute.
Yeah, am I still on mute?
We can hear you now.
Yeah, we can hear you perfect. Yeah, we can hear you fine.
Okay.
Yeah.
So aluminum in additive manufacturing is actually a pretty big business. We did not focusing on aluminum before because purely aluminum has all the fabrication technologies around it, and it's easy to machine, easy to fabricate, and so we never paid attention to it. Then I realized there was so much increase on aluminum, and so we still don't do much of the regular aluminum, other than we do some specialty aluminum for a lot of specialty applications. But aluminum is a very big business, and now we're doing these similar things to Simon's work. We were evaluating and helping the companies producing those high-strength aluminum. We develop their parameters and trying to industrialize their material. It's extremely challenging.
Very, very interesting. Very interesting. So Simon, maybe you want to share some feedback about what Yuping has just said.
Yeah. Before we created our own, or was motivated to create our own material, we were also sourcing a lot from some of these startup companies that I've shown or showing on screen now. And there are two big, I would say, barriers. One is, like you can describe, process parameters was very difficult, and depending on the expertise. I'm hearing some news in the background.
Yeah, somebody has a radio.
So yeah, process parameters, depending on the how experienced one is with the design of experiments for aluminum. It takes some practice. So it certainly was the case for us. We took a lot of practice to really hone down on the right process parameters that would suffice for us in terms of build speed, but also material integrity. We've found that if we want to build with a higher layer thickness, for example, so then we can use a different cut of the particle size distribution of the powder for cost reduction purposes. We see a reduction in properties. That's generally the trend. You know, it really takes a lot of work to hone down on a set of parameters that are that meet, you know, the property requirement, but also the production rate. Expanding a little bit more on supply chain, a lot of the proprietary aluminum, like you know, some of these companies, a lot of startup companies, they either have a joint venture or some sort of contract with a powder maker to create their own materials. So as the ultimate consumer, like on the very right of that that chain, if I want to 3D print or use one of these proprietary materials, I have to wait for, you know, this contract, right, to happen between the startup and the powder maker, and the powder maker needs to have enough, you know, confidence in this startup company to invest and dedicate one of their you know, atomization line to create their own proprietary customized cocktail or recipe, and then they sell it back to us. So that that supply chain, that time period takes very long. So you know, at the end we just thought, okay, well, can we try and make this on our own?
On your own. Very good, very good. I would like to Juan Vega or Andres Manrique, if you have any question or any comment, you are cordially invited to go ahead with that. You have, oh, Juan, you are raising your hand, so you can talk now.
Hello, Julio, can you hear me? Can everybody hear me?
Yeah,
Great.
very good, very good. Go ahead, Juan.
Thank you very much for your presentation. It's really interesting. Actually, it's a topic I am really interested in. So I have a question regarding powders. So usually 3D printing, powder-based 3D printing has this problem. I will put it like a problem that, you know, the feedstock material, the powders, are usually the hardest thing to attain. Like, they are expensive, they are difficult to manufacture, and sometimes, you know, the processing parameters of the SLM machine or the EVN machine can also make you or search for some properties from the powders that sometimes they are not attainable. How do you see the technologies regarding powders in 3D printing? That would be my question.
Yeah, that's also a great insight, Juan. That the supply chain, touching back, is a big area that it can also, you know, need or have improvement in. So an example that I would give on how we tackle this problem in terms of cost is, you know, we look at the typical particle size distribution that's commercially available, right? Like the 15 to 45, that's one common cut, and then the 20 to 70 micron is like also another cut, and they are selling for a, like you said, a high cost because, you know, their whole atomization process, and I'm assuming that powders are made by gas atomization, they can only sell you, you know, say 40% of the yield, right? If you look at the entire production of powder, they only sell you, you know, 410 or 40% of this entire yield. They have to make up their losses by charging you more. So what we did was we went to the manufacturer and we said, well, hey, well, what if you increase this gap, you know, this, you know, the D10 or the 10th percentile and 90th percentile, you know, instead of say 20 to 70, can we go to 20 and 90 or even more? Or like how much can we widen our allowables so then we can get more, we can buy more of their yield, right? that would reduce their cost or the overall cost that we have to bear. So that's one thing that we did. A lot of national, I think they're industry labs. They've started to look into how to change the different designs, components of the components in the powder atomizer to make, specifically, the 20 to 63 PSD range. So let me back up. So there are two school of thoughts here. One is, how can I utilize more of the total yield with the existing technology, right? There are groups that are looking into how can they revamp the technology to increase the amount of powder within that range, those constraints. So I'll give an example of Ames Laboratory. They have their own customized designed ejection or nozzles that could be, that could replace this existing, the current, gas atomization or gas atomizer nozzle. So then the yield, the overall particle size distribution is now, say, 80% from 20 to 63 or 20 to 70 micron range. That means, well, they're no longer selling 40% of the material, right? Like the powder maker, they're selling 80%. So that, again, would reduce the cost of the overall powder and your cost as a consumer.
Very good. So why would, if they are increasing the efficiency of their process, right? Why would they be willing to pass you some of their savings? I mean, if somebody is providing a product or a service and they increase their efficiency, usually they want to use that, translate that efficiency in more revenue profit, right? So what would be the motivation for a company that is increasing its process efficiency to actually pass that saving to the client? Could you articulate a little bit around that?
Sure. I don't want to trivialize that question by
Right.
simply answer supply and demand, but
yeah,
I think that is what I've seen as the case.
Yeah.
From my own experience, purchasing powder for the past 5 years, being the guy in charge to buy,
Yes.
I go out and I look at different vendors and I ask, well, how can you lower the price? Like here, and then we work together, right? So as more people like me are entering the market and are making decisions with, and going with this decision with the cheapest supplier,
Yeah.
right? There's inevitably going to be this increase in supply, which would drive down the cost.
Very good.
And that's
very
literally what we have seen in the past, 3 years. I've seen personally new nozzle designs that really increase that yield, and more people making aluminum. And I can name some of the vendors off the top of my head, but I've seen that there's a lot of movement in that space to lower the cost of the raw material.
Very good. Very good. So Andres, you have randomly been chosen to be the last one to ask or make any comment. Please go ahead if you want.
Okay, thanks, Julio, and thank you, Simon. I know a little bit more about the uses that aluminum has. I didn't know that has too many uses, but I would like to know maybe when you are printing, sometimes you have some pores or internal holes that can affect maybe the mechanical properties. So I would like to know if with that happens with aluminum when you are printing. I don't know if that happens.
Yes.
Yes. If I'm understanding correctly, you're asking if there are channels that, or not channels, but maybe areas
Voids.
that powder is like trapped.
Right. No, what he's trying to say is that if when you are 3D printing aluminum, if you get voids, bubbles in the parts that you are printing, and how you deal with that?
Yeah, great question. Couple ways. One is to really taking a keen eye on the powder feedstock, so the amount of oxygen. So yeah, I mentioned earlier that these defects are usually caused by some sort of well, the industry calls it spatter. But if you do a chemical analysis on this material, there are some sort of oxide or carbides and organic compounds. So if you start out with the raw material that, hey, like, the oxygen, if you give the supplier a upper limit of how much oxygen that you can allow for, or carbon in your material, you can expect the end product to print with less of these spatter. Actually, I think there is a ASTM standard now that talks about the or that gives a spec on the amount of oxygen that you can have in titanium. Titanium being the most sensitive to these oxygen phases forming. I think alpha case is a common one, which causes embrittling effect in your printed material. So that's important to the biomedical industry and the aerospace industry. So there are current specs now that really recommend the upper limit of how much oxygen in this case you can allow. In terms of aluminum, we also take the same approach. We talk to the manufacturing and we try and reduce the amount of oxygen that in the material that we receive. Secondly is in our process parameter, in our process, I would say in the machine. So in a lot of our 3D printers, we can choose what gas to feed in to inert or to fill our print chamber. So the grade of gas that you can select and choose to use matters also, right? If you Google air gas or Linde, a gas company, you can see different grades of inert gas. So we have the print aluminum in inert gas, but with the inert gas, there are different grades of purity. So 99.9, 99.999, and the more pure, the more expensive, of course. So you choose. You as the customer, you choose what you can live with. And that's how we would control the what we've made to attempt to control. The other is what Matt said is how do you control from the source, from the powder, right? So is it redesigning a new chemistry that is more inert? That is definitely a topic to investigate.
Good. So
Thanks.
I thank you for your question too, Andres. So I feel like we have invested a good amount of time and effort in this presentation. Since I have, let's say, facilitated this, I want to express our appreciation and thank you to Simon for the time he has put to put this together. I also want to thank you all the attendees. Some of the follow-up activities is my company will make sure that we put this video in an appealing format. We have recorded the presentation and we will post that in YouTube. We will give you the link. Please feel free when you receive the link to share that with your colleagues, so we increase the awareness about this. I will also send you an email so we stay in touch. If possible, please subscribe to the LinkedIn page of Cambridge Research and Technology. Visit the page. We will try to grow this group and increase the awareness about this topic. I would like to give Simon the opportunity to be the one who actually closes the meeting. After all, he's the one who has delivered the presentation. Please, Simon, take all the time that you want to close the meeting.
Sure. Yeah, I just just like to give the closing remark that I'd like to thank everybody for their time. And I had a lot of fun, and I hope to see each one's names and faces again in the near future, and continue this dialogue. So yeah, thanks again, all, and Happy New Year.
Very good. Okay. Thank you very much to everybody. Good afternoon. Well, good afternoon for me. Good morning for everybody. And see you soon. And please stay tuned because there will be more of these meetings. Okay.
Okay. Ciao.
Okay. Ciao.